All right, let's look at the second exercise. Let's look at the second exercise. So you see that the second exercise is also extremely easy. It's extremely easy. So dans E est égal à R4, on considère les sous-espaces vectoriels F. So F and G sont des sous-espaces vectoriels. And then same, we have F and then the condition that has to be satisfied. For G, we have the condition that has to be satisfied. So it's also a sous-espace vectoriel of R4. You can check. So check if the zero vector of R4 is in F. So the zero vector of R4 looks like this. So 0, 0, 0, 0. So this is equal to, c'est le 0 de R4. It is equal to that vector. So you can check that this is actually going to be, it's going to be in F. You actually have to take x is equal to 0, y is equal to 0, z is equal to 0, t is equal to 0. You see that the condition here is satisfied. 0 is equal to 0, so the 0 vector is there. So you also do the check for the sum, check for scalar multiplication, because they are evident here. It's extremely easy to check. Okay, and here the question has sort of like told you that these are on the sous-espace vectoriel, but here we're just trying to understand why they have said that F and G is on the sous-espace vectoriel, and to sort of like understand how to apply everything that we've discussed so far. So here for G, you just have to take A is equal to 0 to show that G is non-empty. So you see that you have that is going to be a sous-espace. Okay, and if you check the addition, stability by addition and then stability by scalar multiplication. Première question, démontrer que F et G sont en somme directe. Démontrer que F et G sont en somme directe. So how are we supposed to sort of like show that F and G sont en somme directe? C'est très facile. The necessary and sufficient condition in this case is to show that their intersection is reduced to the zero vector. So just like we sort of like did in this, like we solved the previous exercise, how we're going to start solving this one is, well, we'll use the same idea, we'll use the same thing. So because they are subspaces of R4, so what we can do here is soit U, a vector that has 4 components, x, y, z, and t. If we take it from the intersection, like so, intersection of F and G, so this is going to mean two things. This is going to mean that, first of all, that this vector U with components x, y, z, and t is in the subspace F, like so. Now it's also going to mean that this x, y, z, t is in the subspace G, like so. So what does it mean for this vector to be in F? Well, it means that it satisfies this condition. It satisfies this condition. It means it satisfies this condition. So the first condition is x plus y plus z plus t is equal to 0. So it satisfies that condition. Okay, that's fine. That's okay. Then what does it mean for this vector to be in G? Well, it means that it has to satisfy the condition for G. It has to satisfy the condition for G. So the condition for G here says, that here every vector is written in this form, right? Every vector is written in this form. Every vector for G is written in this form. So here, what we can write is that this vector x, y, z, t is equal to this vector that we have here. So here we don't have like an equation to describe the set G like we have for F. Okay, here we have the general form of the vector, So this is how every vector is going to look like. So with different scalars A taken, with different scalars or different values of A taken. So this is how the vector is going to look. So that's why I'm equating. So I'm going to say this is equal to 2A minus A. Maybe I should give myself some more space here. So this is equivalent to saying that the vector U, maybe I can just say the vector U is equal to 2A minus A and then 0 and then A, like so. So this is what we have. So here we can sort of like simplify things. Because for G, if X, let's continue here. So here, it means that the X is going to be equal to the 2A. then it also means that the y is also going to be equal to minus a. Then it means that the z is equal to 0. Then it also means that it also means that, so from the second one, we can conclude that x is equal to 2a, y is equal to minus a, z is equal to 0, and that t is equal to a. So let's get these values that we found. Let's plug them in here into this first equation. Let's plug them into this first equation, like so. So c'est très facile. So here you get 2a minus a. If you plug in z there, you get plus 0. Then you plug in t there, you get a. Well, this is going to be equal to 0 according to the this is equal to 0 according to the first equation. We've just plugged in the values. So here 2a minus a is actually a plus 0 plus 0 again, and then plus a, plus 0 plus a is equal to 0. So a plus a is 2a is equal to 0. So this means that a is going to be equal to what? This means that a is equal to 0. So if a is equal to 0, we found the value for a. So here, if a is equal to 0, this is going to become, so x is going to be equal to 0. And then if a is equal to 0, y is going to become 0. Z is already 0. But then it means that t is also going to be 0, like so. So this vector u that has components, x, y, z, t is going to be equal to the 0 vector. 0, 0, 0, 0, like so. Okay? It's going to be equal to the 0 vector. So this means, because our choice of this vector x, y, z, t is arbitrary, so it means that we can safely say that the intersection f and g est réduit au vecteur nul. Réduit au vecteur nul. Au vecteur nul. So what this is going to mean is that if it is reduced to the 0 vector, it means that alors d'où f et g sont ensemble direct. F et g sont ensemble direct. Sont ensemble direct. Like so. Okay? So that is for the first question. Bien. Exercise number 2. Soit x, y, z, t, a vector in R4. Now we're saying déterminer la valeur de A tel que le vecteur x moins 2a, y plus a, z, t minus a is a vector in F. So find the value of a such that, that is going to sort of like mean that this vector that we have here is going to be an element of F. So this is also an easy question. So why is it easy? Because we already know the condition that a vector must satisfy to be in what? To be in F. We already know the condition. It is this condition. X plus y plus z plus t is equal to 0. That's the condition that sort of like ties everything. That is the only condition that is going to sort of like, help us determine if a vector is in F. Okay, so what value of a must we choose such that this vector that is here should satisfy this condition? So what value for a must we choose? So this means that, you might have maybe gotten the idea here. So for this vector x minus 2a, y plus a, like so, and then y plus a, what is the other component? Z, and then the other component is t minus a. For this vector to be in F, what does it mean? For this vector to be in F, what must happen? So it means that this x here, so the condition, let me just write the condition. We have x plus y plus z plus t is equal to 0. This x, that x minus 2a, that this x component here has to be substituted here. This y component has to be substituted here. The z component has to be substituted here. The z component has to be substituted here. And then if I take the sum, it must be equal to 0. That's the only condition we have for F. So this is going to mean that, so we're going to take this from F. So take, you can say if you want, take, instead of saying for, so that things are a little bit clear. So take this vector. We're going to take this vector from F. So we'll suppose that this vector is in F. Because we're supposed to find the value of A. So we're supposed to suppose that this vector is in F, and then we'll try to solve the equation that we're going to get. So we suppose that this vector is in F, and then this you make the changes that I've written here. So you're going to get x minus 2a plus y plus a plus z plus t minus a is equal to 0, like so. Okay, so we sort of we have to make a the subject to the formula. But first of all, we can sort of group the like terms. So we can group minus 2 plus a will give us minus a. Okay, hopefully that is clear. Hopefully that is clear. Minus 2 plus a will give us minus a. Minus a will give us minus 2a, like so. And then plus x plus y plus z plus t is equal to 0, like so. So this is going to mean that 2a is going to be equal to x plus y plus z plus 2, like so. So you can add 2a on both sides, and then you get what I have here. So our goal is to make a the subject. So a has to be equal to x plus y plus z plus t, like so, divided by 2. So this must be the value for a. So if a is equal to this value, then this condition is going to be true. I mean, then this statement that is here is going to be true. If a is equal to this value, then this vector x minus 2a y plus a z t minus a is with those components is going to be in F if we choose a is equal to this. So this is what we're supposed to sort of find. Okay, we're supposed to do. So then exercise number 3, point number 3 is saying on déduit que f et g sont supplémentaires. Before we even answer the third question, we'll sort of understand this first term that we have here. On déduire. On déduire. It means from the previous result, deduce that f et g sont supplémentaires. So what is the previous result? The previous result is that a has to be equal to this value for f for the vector x minus 2a y plus 2a z t minus a to be in F. Okay, now I understand that I have to sort of incorporate the previous value, the previous value, because the question here is saying on déduire que, so meaning we're supposed to incorporate the previous result to be able to answer the current question. So what are we supposed to do for us to show that deux espaces sont supplémentaires? Well, the first thing that we're supposed to do is that we're supposed to show that f, this sum f and g are supposed to be en somme directe. So this means that f et g sont en somme directe. And then if we show that this is actually true, then we show that the entire space, the parent space, E is going to be equal to f plus g. Okay, is going to be equal to equal to f plus g. So we've already shown that f and g sont en somme directe by showing that their intersection is non null. I mean, that by showing that their intersection is reduced to the 0 vector. I've already shown the part for somme directe. The only thing that's left for us to show is that every vector that I choose in A is going to be decomposed. Uniquely as. So supplémentaire means this. Supplémentaire means every vector in the parent space can be decomposed into two components. One component in the first sous-espace, which is F, and then the other component in the second sous-espace. And then this decomposition has to be unique. That is what supplémentaire means. Okay? So we're supposed to, but here we've already shown the part for somme directe. The only part that's left for us to show is that a vector in E, every vector in the parent space can be decomposed into an element of F and of G. Okay, that's what we're supposed to show. Now let's use the previous result. Let's use the previous result. So I want to show what is the goal before we even use the previous result. Maybe let's look at the goal. Our goal is to say we're going to choose. Now the procedure we're going to take here is procedure. Maybe let me just say procedure to solve this question. The procedure is first step is to take this part we've already done it. Okay, we've already done it. exercise number 1. We've already done it. Exercise number 1. Then the procedure here is to take, we're only left with this part. We're only left with this part. Only left with this part. That every vector that I take from E is going to be decomposed into a component of F and a component of G. So we're going to take a vector. We take a vector in E. We take a vector in E, and then the second step is going to be to sort of like decompose the vector into a component. So this is what you do for any question where they ask you about supplémentaire. First of all, show somme direct, meaning the intersection is le vecteur nul, and then you decompose every vector and then you try to decompose every vector in E into a component of F and a component of G. So into a component of F and G. That's all. So let's look at now how we can use the previous result. Look, so we're supposed to use the previous result, right? So from the previous result, we are saying A has a specific value. So let's say posons A is equal to X plus Y plus Z plus T divided by 2. Okay? Or you can say prenons if you want. Prenons. I think that's better. Whatever. So prenons A is equal to X plus Y plus Z plus T divided by 2. Okay? So this A is a real number. This A is a real number, right? So you don't sort of like confuse things here. A is a real number, it's a constant. Okay? A is a constant. So A is not a vector, it's a constant. Right. Okay? So A is a real number, like so. Prenons, so we take A is equal to this value. So, and then soit, let's take soit the vector U that has components X, Y, Z, and T. We take this vector from E. Here our E is R4. So I'm performing the first step. Take a vector in E. So I take a general vector. A general vector in R4. So a general vector in R4 is written with this it has these components. A component along X, a component along Y, a component along Z, and a component along T. Okay? So I'm performing the first step. Then I need to decompose this U into a component in F and into a vector in F and a vector in G. Oh, look, here I have U is equal to this value. U is equal to this vector, so X, Y, Z, T. Now from the previous question here, we've seen that if we take A as this value, then this vector here, this vector X minus 2A, Y plus A, comma Z, comma T minus A is an element of F. So if I write this here, I'm going to have, X minus 2A, Y plus A, and then Z, and then T minus A. This is an element of F. So this is an element of F. Because my choice of A is this value, it means that automatically, according to the second question, this vector here is an element of A. Now, what vector must I put here? Such that if I add the two vectors, I'm going to get this vector that is on the left. C'est très facile. Now, this second vector here doesn't have to be a component of F. It's a must that this component has to be, it's a must that this vector has to be an element of G. Because we have to decompose this vector in E. This vector is in R4. We have to decompose this vector in R4 into a vector in F and a vector in G. So we already have a vector in F. So we're only left with a vector in G. Oh, we know that every vector in G obeys this relation. Or every vector in G has these components, 2A minus A, 0A, like so. So you can see that if I just inject this here, and say 2A, like so, minus A, and then 0, and then A, like so, if you add these two vectors, you're going to get X, Y, Z, T. So we've shown that because my choice of this vector U is arbitrary, we've shown that this vector can actually be decomposed into an element of F and an element of G. And so here we've shown two things. The first thing that we've shown here is that they are supplémentaires. So meaning F, the intersection, is le vecteur nul, and then we've shown that E is equal to f plus g. So this is what we've shown here. So this means this is also equivalent to saying that f et g sont supplémentaires. Supplémentaires. So this we proved this in the first question. Then we've proved this. We've proved this in the exercise 1. Then we've proved this in this same exercise, exercise 3. So all right. So hopefully that was clear. And be sure to watch the video as many times as possible to sort of like understand what is happening here. So I'll move to the next exercise.